and welcome to this presentation, which is all to do with trigonometry. We're going to review what we've learned at GCSE, both in terms of right angle triangles and non-right angle triangles in this presentation. So our starter task is for you on your whiteboards or on a bit of paper. Can you find the missing sides and angles of these triangles? They're all right angled using any methods that you've learned at school. So pause the video, work out the lengths of the sides and the angles, and then when you're ready to be given the answers, just press play again. Okay, so these are the answers for the triangles. I'm not going to go through the solutions to any of them, but they're all written to three significant figures. And there we have our answers. So any problems with those, then have a go at another go at them, or ask for some help from your classroom teacher. Okay, good. So other than using trigonometry to work with right angle triangles, you've also learned at higher level GCSE how to work with non-right angle triangles. And this presentation is mainly to do with those ideas of sine rule, cosine rule, and finding the area of a triangle using trigonometry. I'm going to start with the first of those, which is the sine rule. And unlike at GCSE level, where you probably haven't derived the sine rule, I'm going to spend a little bit of time going through where that sine rule formula comes from. So here we have our non-right angle triangle. It can be any type of triangle, but we've got angles that are denoted by capital letters of A, B, and C, and we've got the sides that are opposite those angles denoted by little a, b, and c. And what I'm going to do to derive this formula is I'm going to show the perpendicular height of this triangle using B as the base. And if I concentrate on the right hand side triangle, we notice that it's right angled. So I can use SOHCAHTOA, the skill that you've just been using on the starting slide, to work out a value for sine A. So sine A will be opposite over hypotenuse, which will be h over c. And if I rearrange that formula, I can rearrange it, bring the denominator up to the left hand side so that c sine A equals h. Similarly, if I look at the left hand side right angle triangle, I can work out a ratio of sine c. And again, if I use opposite over hypotenuse, I will get a ratio of h over a. And again, I can bring that denominator up to the left hand side, and it gives me my equation a sine c equals h. Now that means that I have two separate equations now that both equal h. So what I've done here is I've put the two together, and then I have rearranged the equation in order to give me sine a over a equals sine c over c. So I've divided both sides by a, and I've divided both sides by c. And this, of course, is the first pairing within the sine rule formula. But we also know that there is a third ratio within the sine rule formula, which is sine b over b. So I'm going to show you where that comes from as well. So what I've done here is I've drawn a perpendicular, but using side A as the base. So I've done exactly the same, but it allows me to get a ratio for sine b. And the right angle triangle is there. We can see it highlighted. So sine b would be opposite over hypotenuse, which is d over c. And in a very similar way to before, if I rearrange, I can have that written as c sine b equals d. If I take the other right angle triangle within here, within this diagram, I can use SOHCAHTOA again to get a ratio for sine c. So sine c would be opposite over hypotenuse, which in this case would be d over b. Rearranging once again as before gives me b sine c equals d, and using the same technique as we did for the first equation, we can produce ourselves another equation where c sine b is equal to b sine c. And if I rearrange that by dividing both sides by C and both sides by B, then I end up with another pairing, which is familiar to us because that's part used in our sine rule formula. And then finally, if I look at the first equation that I generated, and if I look at the second equation that I generated, I notice that they are both equal to sine C over C. And for that reason, I can now put the two equations together and create my sine rule formula, which you have used on your higher level GCSE course. Okay, good. So now that we've derived it, we can write that formula in our notebooks. Now you'll notice that there are two variations here, and I would imagine at GCSE level you will have used both of these versions. If it is an angle that we are being asked to find, then we generally use the left-hand side version, and if it is a length of a side that we are trying to find, then generally we use the right-hand side version. But they're both the same as each other. They have just had their fractions reciprocated to form the second version. The reason why we generally have two versions is because it's much easier to solve an equation if the unknown is at the top, and therefore that is why if I'm trying to work out an angle, I would use the left-hand side version, and if it's the length of the side that I'm trying to find, I would use the right-hand side version. So here is a typical sine rule type question which you can sketch in your notebooks, please. And what I want to just mention at this point is, why am I sure that sine rule can be used to work out the answer for this angle shown as theta? And the reason being is because I have an angle and its opposite side given here, 62 degrees and 56, and I have an angle and its opposite side here shown in the diagram as well. Now it doesn't matter that one of those values is an unknown, but to have that double pair of angles and sides opposite the angle means that I'm going to be able to use sine rule. So the first thing I would do is I would write down the actual sine rule formula. Sine A over A equals sine B over B. Not particularly interested in which side is A, which side is B, which angle is angle A, etc. As long as I've got that double pairing of angles and opposite sides, then I'm fine to use sine rule. I'm then going to fill in the gaps. So sine theta over 38, that's that pairing of angle and side, will be equal to sine 62 over 56, and then it just becomes a case of solving that equation. So rearranging, I end up with sine theta is equal to 38 times sine 62 over 56. And then if I work through that and get myself a decimal, and inverse sine of that decimal ends up being 36.8 degrees. Here is another version. So this time I am wanting to find the side that is side x, and we might be unsure whether sine rule is allowed to be used to work out the value of x, but in this case again sine rule is okay to be used. I've got the angle and the opposite side again here, 47 and 120, but I don't at the moment have the angle that is opposite side x. But that's not to say that I can't use sine rule, it just means that I have to work out this angle down here before I can use sine rule. And the value of this angle that is down in the bottom left hand corner is easily found, because we can't forget that all angles in a triangle add up to 180 degrees. So it turns out that the angle that is unknown is 61 degrees. I can then ignore the 72 degrees. If you would want to cross the 72 degrees out at that stage, then feel free to do so. But I've now got the 47 and the opposite side. I've got the 61 and the opposite side, so it's okay now to use sine rule to find the side x. So again, I've written down the sine rule. I've replaced my unknowns, and it's just a case now of rearranging that equation in order to find the value of x. And if I do that correctly, make sure that your calculator is in degree mode. If I do that correctly, I end up with a value of x of 144. Okay, so that's sine rule completed. We've looked at an example where we needed to find a missing angle. We've also looked at an example where we needed to find a missing side. I'm now going to move on to cosine rule. And again, I'm going to spend a minute or two just deriving the formula, because it's very rare that we do derive the formulae at GCSE level, and it is quite nice to know where those formulae come from. So here we have our triangle again with angles and sides shown as before, and I'm going to draw in my perpendicular height using B as the base. So I'm going to call that length h, and I'm also going to have a value of x, which is the length of the side shown on this right hand side right angled triangle. So using that, I can now work out the ratio of cosine A. So cosine A would be adjacent over hypotenuse, which will be x over c. And very similar to in the last derivation, we can bring the denominator up to the left hand side, and we end up with c cosine A equals x. While we are using this right angle triangle, we can also derive another formula from it, which is that c squared is equal to x squared plus h squared. So that's using Pythagoras theorem, and that gives me my second equation. And if I rearrange the equation, I can write it as c squared minus x squared equals h squared. Now I'm moving over to the left-hand side triangle on my original diagram. And what I do know about this left-hand side right angle triangle is that the length here to here must be b minus x, bearing in mind that b was the total length across the bottom and x was this length here shown on the first triangle. So using Pythagoras theorem again, we can write down that a squared is equal to b minus x squared plus h squared. And this is what's going to formulate my cosine rule formula. So the first thing I've done is I have multiplied out the brackets. So b squared minus 2bx plus x squared plus h squared. I then can take my h squared equation and replace it into where h squared was within my new equation. And then I can see that the x squareds cancel to leave me with b squared plus c squared minus 2bx. And then finally, using the equation that I found out right at the very top of the board, I can replace x within my cosine rule formula, and I end up with a squared equals b squared plus c squared minus 2bc cosine A, which is our cosine rule formula. So feel free to write that rule down now in your notebooks, and we'll have a look at a couple of examples of when we can use cosine rule to find either the length of a side or the size of an angle. So here's our first example. Now you will notice I can't use sine rule for this question like I could with the previous two, because I've only got one of the three angles given to me within the triangle. So sine rule is out of the question, but what I do have is I have an angle which is 66 degrees, and I have the two sides that are either side of that angle. So we have 24, 31, and the included angle of 66 degrees. And because I have those three things, I can find the length of the third side using cosine rule. So I'm going to first of all write down my cosine rule. Again, I'm not so fussed about which angle I'm going to call A, B or C. So we only need to have one version written down. What I must make sure, however, that I do is that if A is my angle 66, so if capital A is 66, it's important that we have X as my small a. So it does make a difference with the cosine rule where I put my values within the cosine rule. So I'll say that again, if 66 degrees is my angle A, then my opposite side, which is X, will be my small a inside the formula. So 24 and 31 are my values for B and C. They can be written either way round. And I can now type that into my calculator to give me a value for x squared. And then finally, let's not forget to square root at the end to give me my value of x, which I've written down to 3 significant figures. So here's example number 2 for the cosine rule. This is where we have a triangle where we know all 3 sides and we are being asked to find one of the angles. So again, the first thing I'm doing here is writing the cosine rule down. And again, it's important that I get the value of A correct here. So the angle A that I am trying to find on my diagram is theta. So it's important that I choose little a to be 32. So when I'm replacing my values inside the formula, it's important that A is 32, but the B and the C can be either 63 or 58 or 58 and 63, it doesn't matter which way round, but the 32 is important to get right. So then I'm going to work out the values a little bit at a time, not trying to do too much all at once. So I've squared all of the values and multiplied together the 2, the 63 and the 58. And then taking the 3969 and the 3364 across to the left hand side. And then I'm doing my division. And then finally inverse cosine of this fraction will get me back to the angle that I need, which ends up being 30.3, and again that's correct to 3 significant figures. The other option for us, if we are being asked to work out an angle like we were in the last example, is to rearrange the cosine rule first before we then start subbing values in. So at school, at GCSE, you may have been taught this process, so I'll just spend a minute going through it just in case you're happier to use the rearrange formula and then sub the values in rather than the way that we've just done it for the previous example. So taking my cosine rule, I can rearrange to give my new equation as 2bc cos A equals b squared plus c squared minus a squared. And then if I divide both sides by 2bc, that gives me an equation that I can sub the values into in order to get the angle A perhaps a little bit more straightforwardly. But it just depends on whether you were taught this at school or whether you were taught to just put the values in and then rearrange at the end. Either is good. You have to decide which way works best for you. Okay, so we often get asked the question, well, when would I use sine rule? When would I use cosine rule? There's sometimes a little bit of confusion as to which rule is best to use for which question. So there's quite a simple guide to ensuring that you're going to use the right method for the right question. So the first question you ask yourself is, do you have two angles, or do you have any known opposites? And we talked about those opposites when we were dealing with the first question for sine rule earlier on. And if the answer to that is yes, then you would use sine rule. And there are, as we've said, two versions depending on whether you're looking for the length of a side or whether you're looking for the size of an angle. And if the answer to those questions are no, then you would use cosine rule. And we've looked at the original version of the cosine rule and also the rearranged version, which some of you might use to find an angle. Okay, so the last thing I want to look at before we move on to the area of a triangle is we call it the ambiguous case. So here we have a triangle with lengths of sides 8.1, 3.2. We've got 21 degrees, and we are then being asked to work out the value of theta. And we're going to use sine rule for this question because of those known opposites that we were talking about earlier on. So we've got the 21 degrees and the opposite side of 3.2. We've got the angle theta and the opposite side of 8.1. So this would be a classic example of the use of sine rule. And because it is the angle that we are being asked to find, then I am going to use this version of it. And I am going to replace the values that I have in my triangle into the sine rule formula. So sine theta over 8.1 is equal to sine 21 over 3.2. And I'm going to work through this and find that sine theta is equal to what you're seeing here. And then finally, when we do the inverse sine of the resulting value, we get an answer of 65.1 degrees, which is fine. But if you look at the diagram, you will notice that this is not 65.1 degrees, our value for theta that we're trying to find. It's clear from the diagram that it is an obtuse angle that we are being asked to find, and we have found an angle that is acute. So what's going on? Well, the maths isn't wrong, you've done everything right. The problem that we've got here is that the details that we were given for the original triangle means that we can draw that triangle with those details in two different ways. So this is called the ambiguous case for sine rule. So if I show you the diagram that looks like this, you will see that this is the alternative way that I could have drawn a triangle with the details that I was given. So this triangle also has lengths of sides 8.1 and 3.2. It also has an angle of 21 degrees, and you will see that the value for theta that we found of 65.1 fits in really nicely with this triangle. So we have to make a change in order to find the value of theta that we actually want, the obtuse angle. So how would we find that value of theta which is obtuse? Well, it's quite simple. This triangle that's in the top right hand corner of the screen is an isosceles triangle. Both of those lengths are 3.2. And therefore, if both of those lengths are 3.2, then it means that the angles at the base of the triangle are both 65.1. So there is the 65.1 drawn on my diagram. And then to finish off, that means that angle theta that I am looking for will be 180 minus 65.1, which equals 114.9. So this is a nice little special case for sine rule that we often see at A level, and be careful and look out for it. So the way that the examiner will often indicate that there is an ambiguous case is that when they're asking for the angle, they will often say find the obtuse angle for theta, or they might say find the acute angle for theta. So if it's the acute angle for theta that we're looking for, then the one that we found originally would be the right one. And if it is the obtuse angle that we are being asked to find, then we simply take that 65.1 away from 180 degrees, and that will be our final answer. And quite often, if it is the obtuse angle that they're wanting from us, they will often put the word obtuse in bold. So look out for that. It means that we're looking at the ambiguous case for sine rule, and it's quite a nice little question to be asked at A level. Okay, good. So that brings us to our final formula that we're going to need to use for our basic trigonometry at A level, and that is the alternative for the area of a triangle. So we already know the area of a triangle is found using half times base times height, but there is also a trigonometry version for that formula as well. So we can derive it using the same sort of skills as we use for deriving the sine rule and the cosine rule earlier on. So first of all, this is our traditional formula for the area. But in the same way as I drew the perpendicular height for the sine rule and cosine rule, I've done that again for our final formula that we're looking at here. So in the same way, sine C, I'm using the left-hand side right angle triangle. So sine C would be opposite over hypotenuse, which is h over a. And once again, if I bring that denominator up to the left-hand side, we end up with h, the height of the triangle, equaling a sine c. And if I simply go down to the bottom, the original formula of half base times height, and replace that height with a sine c, I end up with my new formula for the area of a triangle, which uses trigonometry rather than the base and the height of the triangle. And there we go. So the area of the triangle is found by working out a half AB sine C. And again, it's a bit like the cosine rule. If I want to find the area of the triangle, I need angle C and I need the two sides either side of the angle. So if I was using angle A, I would need sides B and C. If I was using angle B, I would need sides A and C. And if I'm using angle C, then I need sides A and B. So by all means, as you did with sine rule and cosine rule, write this down in your notebooks, please, and we'll have a look at an example of that in action. So here is that example. I've got an angle of 68. I've got lengths of sides 12 and 19, and they are the sides that I need in order to use this formula. So all I'm going to do is write down the formula, substitute my values of A, B and the angle C into that formula, and then simply work that out using the calculator. And it comes out, three significant figures, as 106 meters squared. Okay, really good. So we've now finished sine rule, we've finished cosine rule, we've finished area of a triangle using trigonometry. The only thing left to do now is to practice those skills. So there's two ways we're going to do that. We're going to have a look at an exercise from the textbook in just a minute, but first of all, here's a nice little exercise that you can do on a whiteboard or on a bit of paper, and that is to find the missing angles and the missing lengths from each of these three triangles, and then confirm once you've done that the areas of the three smaller triangles add up to the area of the large triangle. So it's a really nice activity to do to practice all of the three methods that we've seen today, and you can pause the video, have a go at it, and when you're ready for the answers just press play and I will tell you what those answers are. Okay, so let's have a look at what the lengths of the sides and the angles are that are missing. So 110 for the center angle, because all the angles inside or around a point add up to 360. And then the others are as follows. So 28.9 degrees, all of these are to three significant figures. 16.6 for the length of the side. 36.1 degrees. 9.75 for the length of the side, 25.1 degrees, 19.8 degrees, 16.2, and I think finally 34.5. Good, well done if you got all of those right. And then to finish off, we have exercise 1.2 on page 67. It covers all of the ideas that we've looked at in this presentation. So get plenty of practice, and then I will see you next time for the next presentation. Thank you very much.